Imagine a warehouse so vast, the identical cardboard boxes stretch endlessly into the darkness. If you want to know exactly what is inside every single box across the entire facility, you face a physical limit. Measuring them all is impossible. You are navigating with a flashlight that only illuminates a few boxes at a time. We call the true, invisible metric of that entire population the parameter. It is what we actually want to know. But because we can't measure it directly, we are forced to rely on a sample, a tiny observable fraction of the whole. This creates a permanent tension known as sampling error. Because we only ever look at a fraction, no two samples will perfectly match each other. The natural difference between our sample statistic and the true parameter means every sample we pull is inherently limited. Look at this diagram representing a massive population. If a bank checks a sample of 100 loan applications and calculates an average processing time of 5.2 days, did they find the true average of all applications or just a random anomaly? When we sample a different 100 dots, the average shifts entirely. Because our data is permanently incomplete, human intuition is insufficient for accuracy. We need a mathematical framework to quantify our uncertainty and allow us to make confident decisions anyway. That framework relies on a theoretical engine known as the central limit theorem. This jagged line graph represents chaotic, raw data from the real world. It is asymmetrical and unpredictable. But the central limit theorem reveals a mechanical certainty. If you take large enough samples, conventionally 30 or more, from any population, the averages of those samples behave predictably. Watch the distribution of those sample averages. Regardless of how messy the raw data was, the sample averages cluster together to form a perfectly symmetrical bell curve, centering directly over the true population parameter. The spread of this curve gives us a ruler called the standard error. It measures exactly how much uncertainty exists in our sample. Notice that as the sample size increases, the standard error physically shrinks, tightening the precision of our estimate. The central limit theorem converts messy, unknowable reality into clean, measurable probability. With that probability, we can construct a confidence interval, a practical tool that provides a range of plausible values for our unknown parameter. Here is how we build it. On this axis, we place our sample's point estimate, right in the center. We then stretch brackets outward, multiplying a critical value by our standard error to create a shaded zone of plausibility. A 95% confidence interval doesn't mean there is a 95% probability the true parameter sits inside this specific box. The true parameter, the solid vertical line, is fixed. It does not move. The intervals are what vary from sample to sample, and you can see several intervals missing the mark. A confidence interval doesn't prove the parameter is trapped in our specific estimate. It simply quantifies that our method of constructing these intervals captures the truth 95% of the time over repeated sampling. When we transition from making estimates to testing a specific claim, we start with a default assumption. In this schematic, the main pathway represents the null hypothesis. It is the assumption of the status quo, that there is no difference and no effect. We put our sample data on trial by defining the p-value, the probability of seeing our exact sample data if the null hypothesis were absolutely true. This normal distribution curve maps those probabilities, with the extreme tail ends shaded red to represent our alpha threshold, typically set at 5%. If our test statistic drops into this red zone, the p-value is below alpha. The data is mathematically too unusual to be a coincidence, and we reject the null hypothesis. Rejecting the default assumption doesn't definitively prove a specific alternative is true. It only proves the default status quo is highly unlikely to be the reality. Because every test we run is based on probability, our final binary decision, whether to reject or keep the null hypothesis, always carries the risk of being wrong. This matrix breaks down the two exact ways we can fail. A type 1 error, driven by our alpha threshold, is a false positive, like launching a flawed marketing campaign based on noise. A type 2 error, or beta, is a false negative, missing a genuinely beneficial effect that actually exists. The math enforces a direct trade-off. If you tighten alpha to prevent false positives, the scale tips. The math automatically raises beta, increasing your chances of missing a real effect entirely. Data science doesn't offer perfect safety. It forces you to look at your business and decide which type of failure you can better afford to absorb. Our main countermeasure to missing a real effect is statistical power. Power is the test's sensitivity, its ability to correctly detect a true signal against the background noise. This is the risk of testing on small samples. When sample sizes are small, tests are underpowered. It is like trying to spot a massive structure through heavy fog. A genuinely great improvement is obscured by variance, and the idea is discarded because the sample was too small to prove the math. The only mathematical way to lower both the alpha and beta risk simultaneously is to increase the sample size. More data physically shrinks the standard error, sharpening the test's ability to cut through the noise. Statistical inference provides the rigorous framework for quantifying our own uncertainty. It allows us to make the smartest, most defensible bets in an unpredictable world.